Hi, this video is on some extra properties of the conditional statement. Now, you may recall the conditional statement. How is that? That's the statement P implies Q, and that's essentially the statement that whenever P is true, then Q must be true, and if P is false, then it doesn't matter what Q is. And so we'd like to discuss some common misinterpretations today of the statement P implies Q and some common fallacies. So, for example, again, let's give P and Q some real life values to make this contextual. So let's say P is it rains and Q is I get wet. Right? Then in this context, the statement P implies Q means if it rains, then I get wet. Alright, so some common misconceptions are that people have about implication statements like this is they think, oh, if P implies Q, then what must also be true is Q implies P. So therefore Q implies P, right? If it rains then I get wet, then we get wet, so it must have been raining. But that's not true, is it, right? If it rains, then that's one circumstance where you could get wet, but you could also be splashed with water some other way. You get hit by a sprinkler or something like that. There are circumstances in which you could get wet where it didn't involve rain in any way. So just because you're wet doesn't mean it has to be raining. So this is not true. Q implies P is not the same thing as P implies Q. So these are not equal statements. And one way to verify this is if you go ahead and build a truth table for both P and Q implies P, you'll see that they aren't true under exactly the same circumstances. Specifically, the circumstance where this is false and this is true. If P is false and Q is true, this is true. If P is false and Q is true, this is false, right? And in our context here, this is exactly right. It didn't rain, but you got wet, right? And that's exactly what we were just talking about before. If it didn't rain, then whether or not you get wet, this first statement's true. But if you got wet and it turns out to be from something other than rain, then you can't make the second statement that getting wet implies raining, right? That's not true anymore. So this statement here is called the converse of P implies Q, where we switch the two arguments, and this is not equal to P implies Q. Another common statement that people think it's equal to P implies Q, but it's not the same as, is this statement, not P, therefore not Q, right? So their thought is, well, if it rains, then I get wet. If it's not raining, then I must not get wet. But for the same reason we discussed here, that's not true. Let's say P is false and Q is true. That means not P is true and not Q is false. And we have a true implies false statement here, which is not true again. And so this is called the inverse of P implies Q. And we can see again that that just because it rains means that you get wet. If it's not raining, you could still get wet. You're not guaranteed. It doesn't imply that you won't get wet. So the best way to visualize the relationship between P and Q when you have a implication statement like this is something like this. P implies Q means whenever you're inside a situation where P is true, you must be inside a situation where Q is true, right? So the way we would think about this is by saying, well, out of all of the ways you could get wet, it raining is a subset of those. So if it rains, then you're inside the collection of things that could get you wet. But if you're inside the things that could get you wet, you could be in the raining thing. You could also not be in the raining thing. Another good example is if a shape is a square, then it's a rectangle. Right? If you're a square, that's one type of rectangle, right? If you're a rectangle, you might be a square, you might not be a square. That backwards direction is not implied. And then so looking at this, we can see that P implies Q definitely doesn't mean Q implies P. And it also doesn't mean not P implies not Q. If you're not inside the P, you could still be inside of Q. So just because you're not in P doesn't mean that you're not inside of Q. And so just because you know not P doesn't mean you're allowed to conclude not Q. So this and that don't follow from P implies Q. They're completely separate things. All right. So what can you conclude? Well, one sometimes useful equivalence is the statement not Q implies not P. I think I mentioned this in the other video. This is the contrapositive. And what this statement says, look, if you live outside of Q, then certainly you live outside of P because P lives inside of Q. So if P is all of the squares and Q is all the rectangles, and I hand you a pentagon here, well, that's definitely not a rectangle, so it's definitely not a square, right? So if you're not Q, then you're not P. If you didn't get wet, then it couldn't possibly be raining. Here's all the circumstances where you get wet. Here's all the circumstances where it rains, and you're on the outside somewhere being dry. So these statements actually are equivalent, and you could write up a whole annoying truth table to verify that these two are the same. But I'm going to just do this briefly with the logic rules that we had made up from before. Let's see, there's not a lot of stuff written here. So let me say, well, P implies Q. We know that's equal to not P or Q, correct? That's just our very first equivalence of that fact. And what we know about not P or Q is that that's definitely equal to Q or not P, right? I mean, I can switch those two things around and it doesn't make a difference. Then Q is not Q or not P, right? The not Q and Q are the same thing. And finally, we just have not, and this thing becomes Q implies not P. I'm just reverting this equivalence here. So by doing some quick algebra here, we can see that P implies Q and not Q implies not P, that those are in fact the same thing. All right. Then, so, sometimes when people make this implication, like if A happens, then B happens, they want it to also mean when B happens, then A happens. They want it to go both ways. So can we talk about what sort of a statement can be generated from P implies Q and Q implies P? What sort of a statement would hold when both of these things are true? Well, whenever P is true, Q has to be true, and whenever Q is true, P has to be true. Whenever Q is false, the only way that this first statement could be false is if P is false also, and whenever P is false, the only way this could be true is if Q is false, and they both have to be true for the whole thing to be true. So what that tells me is that this is a statement that's true whenever they're both true or they're both false. And this makes sense, right? You want whenever P happens for Q to happen, and whenever for Q to happen, that P happens. And for that to be true, it must be that they're either both happening at the same time or they're both not happening at the same time. There's no other scenario. Otherwise, one of these guys does not hold. So, maybe we'll do one of these very quickly. And then P implies Q and Q implies P. And so our possible initial conditions here are that we have P could be true or false, Q could be true or false. And as we know, first of all, if they're both true, P implies Q is true, and whenever P is true or is false, then the statement's true, and this is the only case that it's false, right? With Q, it's the exact opposite. When you have true implies false, that's false, everything else is true. Right? And now when you take the and statement of these, that's true, so they're both true. Otherwise, they're false. So there we have it. There we have a statement here that's true whenever they're both true or they're both false, and it's false if they disagree. And so we call this operation either the double conditional or the biconditional. And it's denoted with a double arrows to imply the implication in both directions. So it's true or it's false. And the biconditional says, well, when they're both true, it's true. When they're both false, it's true. Otherwise, they're false. And the way to visualize this is, well, P lives inside of Q, and Q lives inside of P. So in order for that to hold, they really have to be the same circle here, right? P and Q are actually the same thing. Whenever P is true, Q is also true, and whenever P is false, Q is also false. You can't live inside of one and not inside the other. And so, as you might imagine, not a great choice here. If I negate this thing, it's going to be true when they're different, and it's going to be false otherwise. So those are just some additional quirky little things about the implication statement.